Hey, good morning, everyone. Welcome to class. And our lesson today, as we had planned, is Introduction to Pressure Relief Valves, their purpose and function.
In this video, you'll get to see Carl teach a class on relief valve basics.
As you add that fourth brick, and we go to 8,000 pounds,
he's teaching the class remotely using screen sharing and video chat.
And be prepared to make some observations and note what has taken place.
By the end of the video, you will have seen how to use our live schematic simulations, and you might even learn a new thing or two about relief valves. Enjoy!
And of course, a relief valve is a very important type of control for hydraulic systems. So maybe before we dive into the material, let's just take a moment and think of why a hydraulic system might even need a relief valve. So just think about that for a moment. And of course, they come in a variety of different shapes and styles. Some are just these little thread-in cartridges. You've seen those, and some have a great big hand wheel. You can really get your hand onto it, and some have a lot of cast iron involved. So they come in a number of different packages. Let's just make sure we think for a moment about why a hydraulic system might even need a relief valve. Anyone have a thought on that? Who'd like to take a shot at that one?
It limits the top pressure that a system can build to.
Hey, that's right, Nathan. Yeah, absolutely. A relief valve can help set a limit to the top pressure for a hydraulic system. And Robin, what do you think might happen to a hydraulic system if the relief valve wasn't there? Can you imagine what might occur?
I think it could blow up.
Hey, there you go. Yeah, we might have a problem where a hydraulic hose might burst. A serious environmental mess. Somebody could get hurt. Our machinery is damaged. These are all undesirable things. So a hydraulic system may indeed need a pressure relief valve to make sure that we don't go over the top. And so that's a really great point. If you guys are all logged into Lunchbox sessions, in the hydraulic menu, let's scroll down to pressure relief valves. And once we're inside the pressure relief valves menu, let's head on down past lessons for now and videos, past the videos, and let's head down to the simulations. And I'm going to start off this morning with the very first one. That is the basic relief valve, direct acting. And let's click on that one. And of course, remember that each one of these simulations only teaches one or two things. They're kept simple on purpose. In this case, we have a few recognizable elements, perhaps. I think in earlier lessons, we've studied that circle that is rotating on the left-hand side is there to be our pump. It's a fixed displacement pump because it's missing that diagonal arrow. So this pump, if it's running, puts out its full flow. This one says it's going to put out 10 gallons per minute. So hey, in your hydraulic system, you better find something to do with that flow. You better create a path or there's going to be trouble that Robin was alluding to. So it's putting out its flow, and then we see a directional control valve over on the right there, those three complex boxes, but let's not worry too much about it. That directional valve is permanently in the on position, and it's making our cylinder extend. So that's our direction, cylinder extension, and of course our cylinder just magically recycles at the bottom every time it reaches the end of stroke. And of course we have a secondary flow path closer back to the pump there, which is the relief valve. And it looks like we've got some relief valve already going through there. Looks like our flow path is already split up. So that's interesting, and we'll come back to that. But for now, let's have everybody move over to the right side of your screen there and set that relief valve to the maximum. Just crank that thing. Move that slider all the way to the right. There is some magic text down here at the bottom near the control knob that says 1000 psi, and it says that's the relief setting. But as you and I know, on a real hydraulic system, there won't be a number floating nearby to tell you what that relief valve is definitively set to. We'll come back to that in a minute. If you remember our lesson about the FBA triangle, where force is on top and then pressure and surface area are beside each other below, we'll remember that the pressure gauge reading that's showing on our system gauge is about the amount of force that our cylinder is exerting, the mass it's moving, which right now is 2,000 pounds. divided by the surface area. So that 10 square inches that's written on the piston there, that's the surface area at the very bottom of the piston, the base end of the piston. So 2,000 pounds divided by 10 square inches is what's currently giving us our system pressure reading of 200 psi. And yes, we wouldn't see any noticeable amount of pressure if the pump was off and the cylinder was resting at the very bottom. But this is an active system, and so we're reading the pressure that it takes right now to extend the cylinder. So go ahead and click on the button that says Add Weight. Let's add some weight, and that's going to add another 2,000 pound brick on our hydraulic brick stacker there. So now we've got 4,000 divided by 10. So that's what's accounting for our 400 psi of system pressure. Go ahead on your end and add another brick. We're at 6,000 pounds now divided by 10 square inches. 600 psi system pressure. And on this very next one, as you add that fourth brick and we go to 8,000 pounds, keep a close eye on everything about the hydraulic system and be prepared to make some observations and note what has taken place. Okay, add that fourth brick. So we're now at 8,000 pounds and divide by 10 square inches. We have 800 pounds per square inch on our system pressure gauge. So who wants to chime in? What did you notice taking place? Did you notice anything interesting happening there? Alex, what did you see happening as we added that fourth brick?
I can see that some leak occurred through the pressure relief valve.
Oh, yes. Okay, correct. So something's already happening. We've got a flow path at the relief valve. Good observation. And anyone else want to chime in? What other observations did you make?
The cylinder starts slowing down.
Hey, that's absolutely right. The cylinder does slow down a little bit. So that makes sense. If some of our flow is headed back to tank through the relief valve, obviously we've divided our flow path, and some of our flow from that 10 gallon per minute pump is no longer being used to extend the cylinder at the same speed as before. Our cylinder is a little slower. So this is a very important observation to make. Okay, this last brick that we're all going to add on there is 2,010 pounds, which one would think is going to induce a system pressure above 1,000 psi. But of course it doesn't, because our relief valve is set to 1,000 psi. And in fact, guys, this is a really important moment to observe something, and that is that when 100% of the pump's flow is passing through the relief valve, whatever pressure is showing on the system gauge, that is now your official relief valve setting. 100% of the pump's flow has to be going nowhere else but through the relief valve to be truly confident about what that relief valve setting actually is. And what did you notice the cylinder doing when we put that last brick on there? What did you see happening there, Ivan?
I noticed that the cylinder sort of sunk back down to the bottom. And one other thing I noticed was that the hydraulic line coming from the pump is now red, whereas when you started off, it was more of a kind of a yellowy color.
Hey, a couple of good observations there. Absolutely right. If the system relief valve is there to protect all of the system and there isn't any other points of blockage in the system, if that directional control valve is still active, which it permanently is in this simulation, then all points in the circuit that can access that junction to the relief valve there near the pressure gauge will be protected. So it makes sense that the cylinder crashed back down because we had so much weight on that cylinder, it was trying to induce a pressure higher than our relief valve setting. But no, we were saved by the relief valve. Okay, other hydraulic systems may find out that there are some points of isolation between the directional control valve and the cylinder, and so another relief valve might be needed called a port relief, but that's for another time. Going back to the pump side, we'll notice that our pressure is at the highest level, which is the dark red color, and right, we see that all of our pump's flow is passing through the relief valve. Now, if we go back and remove one weight, just for a moment, go back and remove one weight, we are no longer at the relief setting. We're no longer at the pressure that everyone's concerned about. This hydraulic system might be dangerous with too much force, or as Robin was saying, something might burst if we were at 1,000 psi. Well, we're no longer at 1,000 psi. We're back down at 800 psi, and some of our flow is still passing through the relief valve, and our cylinder is not moving as quickly as it could. And so you've just seen what are the disadvantages to the type of relief valve that has only one spring and one poppet. And so if you're looking at that cutaway, we're not really into the symbol yet for a relief valve, but if you're looking at that cutaway of the relief valve, what you're noticing is it's really simple. It's just a spring, and you can adjust it. It's just a spring and a poppet. It's not much more than two very key pieces, the spring and the poppet. Would you guys say in some ways it's nothing more than a check valve with an adjustable spring? Because that's exactly what it is. So what you've observed is that it has some interesting properties where when you're working with just one poppet and one spring, that type of relief valve has to be able to stretch back. That poppet has to be able to compress back against that spring over a band of pressures until it's open wide enough to take that pump's full flow. And what we've discovered is that the cracking pressure, which is the point at which that poppet just backs away and starts to divide some of our pump's flow. It's getting into that relief action area, starts at a pressure well below the maximum system pressure that we were worried about. The maximum system pressure we were worried about was 1,000 psi, but here we are somewhere around 800 psi, and we're already cracked open. And somebody pointed out earlier that the cylinder was slower. That's absolutely right. We've lost, in terms of production, you could say our production has slowed down. Undesirable. Can we improve on that? Absolutely. And that is why you'll find out that the vast majority of relief valves that get used for a production system, relief valves that get used as the primary system relief, have more than one poppet and one spring. Okay, so before we move on, does anyone have any thoughts or questions?
You talked about how the cutaway, there's a poppet and a spring, and I can't quite see what the spring is. Would you mind zooming in on that and showing me what part of the cutaway is the spring?
Yeah, let me just, since I'm on a laptop, I'm just going to use my scroll wheel a few notches here. If you guys want to do the same, you can. If you have a scroll wheel on your mouse, use that. Otherwise, you'll find that plus minus on your numbers row of your key bar will work. If you're on a tablet, you know what to do with your fingers. All right, so there we are zoomed in. Is that a pretty good view, Ivan, for you to see what's happening there inside that relief valve?
Is it that sort of series of dots coming down from the poppet?
Yeah, springs, whenever they're drawn in cutaway form, and you'll find this too in the in cutaway diagrams from valve manufacturers, springs end up being chopped up into a whole series of little circles on each side if you cut right through. So yeah, good question. This shows up a lot on black and white drawings you're going to see from Parker or Eaton or something like that when they show you the inside. So yeah, anytime you see that pattern of circles like that in two rows, you're looking at a spring that's been cut clean through. Absolutely. Elsewhere in the relief valves module, you're going to find that there's some 3D views in the lessons and perhaps a 3D video or two, and then things will spin around and you'll see the spring as a whole. Yeah, good question. Any other questions?
How strong is that spring? Can you compress it with your fingers?
Yeah, very good question. Right, so, I mean, it depends on what the normal range setting for this particular component was rated for. So the spring will have a different tension depending on what the manufacturer set as the maximum value for this particular component. But if it is only a single spring, single poppet style relief valve, and it's for a hydraulic system, then it's probably going to be rated for some thousands of PSI, for some hundreds of bar of pressure. And so if you held that spring in your hand and try to squish it, it's going to be pretty hard to do. That's going to be a very stiff spring. And that's why it takes that threaded knob there to push against it with that washer and squeeze that thread against the back side of that poppet. Good questions.
Oh, I would like ask if I approaching equipment and I would like increase system pressure, should I rotate it clockwise or counterclockwise?
Okay, also, yeah, very fair question. You know, it's really good to get acquainted with a pressure valve when it is in the standalone. Like if you can get a hold of that pressure valve before it's installed in the system and get to know it and read from the manufacturer spec sheet, that would be the best and safest way to make sure that what you're doing is correct when you make adjustments to it before you get busy. But the vast majority of hydraulic pressure controls will increase their pressure as you turn the control knob clockwise. There is a really notable exception in the world of the counterbalance valve. Not today's topic. It's sometimes exactly the opposite. But best to be sure by reading manufacturer specifications or find someone who knows that machine really well. Or, you know, if it's a piece of mobile equipment, quite often the manual will be very specific, talking about turning something clockwise to increase the pressure. And yeah, very good question. You want to be sure you're safe before making an adjustment and doing it correctly. All right, let's move on now and let's have a look at this type of relief valve one more time in another simulation. So let's hit back to session. Let's go to the simulations once again. And click on Anatomy and Behavior of a direct acting relief valve. And I'm just going to change the way I see you guys in the menu for a little bit here. All right, so you should see a hydraulic motor turning, and the pump is also putting out flow. And this time on top of our hydraulic motor, we've got a little platform there. And what this platform does on top of the hydraulic motor is it's a brake shoe brick stacker platform. We're using the symbol for a hydraulic motor, which is the dark arrow pointed in. And that way we don't have a cylinder getting to the end of stroke. And it's good to have a look at some hydraulic circuits where pressure needs to be limited, where there's something other than a hydraulic cylinder. So the hydraulic motor is the other very popular actuator to work with. So again, though, a pretty simple circuit. We've only got two flow paths, one through the hydraulic motor, which might be doing what? I don't know, turning a winch maybe to lift some loads, turning an auger to move some grain or materials from one bin to another. Not sure, but a hydraulic motor is a typical actuator to create some rotating force. And we've now got a cutaway over on the right. And what you're going to notice on this simulation is that if you hover over various parts of the relief valve symbol, this is the first time we're bringing the symbol in, right? In the previous simulation, guys, we looked at a cutaway. Now we've got that same type of relief valve. It's still a single spring, single poppet, direct acting relief valve, but now we're looking at it on the left as a symbol. So that gets us used to seeing that symbol, because it's going to show up on a lot of schematic diagrams that you're going to work with when you're out there on machinery. So any point at which you're wondering what these different pieces of the symbol are about, hover over them with your mouse pointer or with your finger and look for the matching piece that lights up over on the cutaway, and you'll get a bit of an idea for what the elements of the symbol are meant to represent in the actual build. Hey, there's that answer about the spring, right? That was a good question before about the spring and the circle. So there's a great way to have some confirmation about that one. All right. So let's have a look again at this action about where the cracking pressure of the relief valve is a lot lower than the full flow setting. So what I'd like you to do is once again go over to the right, crank up your relief valve setting all the way to the top, crank it right up there, and we'll move that relief setting all the way to the right. And then let's take our resistance slider, which is going to start to put a load on top of that brick stacker. Take that resistance slider, guys, and just slide it along until that pressure gauge up there on the cutaway system. Take that slider and just slide it up until you're at 400 and something. I don't care which number, 400 and change for the pressure value on that pressure gauge. And what I want you to observe is down there on the graph. Have a look at that graph. That graph is a PQ graph. It is going to graph the system pressure up the left vertical axis, and it's going to graph the flow through the valve on that horizontal axis at the bottom. And PQ graphs show up in industry both ways. Sometimes pressure is along the horizontal and flow is on the vertical y-axis. Either way, it's common enough. So just look carefully when you're looking at a PQ graph. Q is the letter that's so common for flow. Sorry about that, class. I just throw that letter out there as though it means something to you. But Q is a common letter for flow. And that's what's being graphed across the bottom of the graph there. So what we realize so far is there any flow taking place yet? What do you think, Crystal? Is there flow going through that relief valve just yet?
No, there's not.
No, there is not. There's no flow through the relief yet because we've just got a pressure coming up that y-axis. We can see visually at the live schematic on the left that there's no flow arrows passing through it. We haven't cracked that relief valve open yet. So we've just built up some system pressure. Now go back to your resistance slider and increase till the system pressure is just 500 and change. Doesn't really matter what number specifically, 500 and something. And we see the change that has taken place here. What's happening now? What's changed about the hydraulic system? What's changed on our graph? Who wants to take a shot at some observations there?
It looks like we have some flow now.
Yeah, absolutely right, Chris. We have some flow through the
relief valve.
Yeah, we're actually passing some flow through the relief valve. We can see that clearly by small flow arrows in the live schematic. We can see some white flow arrows on the relief valve poppet. If you want to, guys, scroll or pinch, zoom way in there on that poppet and have a look. You'll see that poppet has backed away just a tiny amount from the seat of that relief valve. So we've reached a cracking pressure. And our PQ graph clearly shows that we've got about 1 gallon out of our, what's our pump maximum there? 20. We've got about 1/20th of our available maximum flow from that pump is now passing back down to tank. We've divided our system flow. So go ahead and move that resistance slider once again. And remember what the resistance slider represents. It's not about us adjusting the valve. We're not doing that. Resistance slider is about us giving that hydraulic motor more of a load. We're using bricks to simplify. Dial it up until, move that resistance slider till you've got about 10 gallons per minute moving through that relief valve, and at least 3 bricks are showing on the hydraulic motor brick stacker. And all we're doing is changing the load on that motor. We're making an auger work harder against heavier material, or our hydraulic winch is lifting a heavier block. Whatever the application is for the motor, it's working harder. And so now half of our pump's flow is going through the relief valve back to tank, and only half remains for the motor. And that motor is slowed down to half. So our production's been cut in half, and it doesn't seem like there's going to be an end to this anytime soon. An end, that is, to the motor slowing down. Okay, so tell me, guys, play with that resistance slider for a minute. Go ahead and you guys experiment with it for a minute. And then you guys tell me, what is the setting of this relief valve? I'm interested in hearing what you have to say about that. Who wants to chime in and tell me what the setting is of that relief valve?
I'd say it's 1,000 psi.
Yeah, quite correct. The setting of the relief valve is 1,000 psi. And Robin, we determined that because what are we observing here?
All the flow is going through the relief valve and none is going to the motor. And that's the value, right?
That's correct. As we stated earlier, once you are confident that all flow has ceased everywhere else in the hydraulic system and flow is only passing through the relief valve, have we discovered what the true full flow setting of our relief valve is. That's the setting at which it will protect you, protect the system from coming apart when all flow paths are blocked except for the all-important relief valve, which is ready to jump into action, is connected directly to tank. Now, let's just state, we're in some very simplistic learning tools here. Let's just state that you wouldn't typically set a relief valve by overloading a hydraulic motor. There would typically be a point of blockage between the relief valve and that hydraulic motor. We're missing a directional valve, we're missing other things. But just so we get that concept straight, once flow can go nowhere else, only through the relief valve, we've discovered the setting of the relief valve. Now, have a look at that graph. On the right-hand side of that graph there, where we see that there's some text there, and you may want to zoom in on it. Here, I'll zoom in on mine for a moment. And let's look on the left-hand side of that graph and discover some terms that are worth knowing anytime you're studying a relief valve. And one is cracking pressure. That was that pressure that we noticed we had to bring the system up to before it even began to open and divert some flow back to tank. So that's one official aspect of the relief valve to note. And the other is at the top. It's the true relief valve setting that we discovered, as Robin pointed out, when all of the flow is going nowhere except through the relief valve. But then there's that third term. It's a new term that we're seeing here, and it's called override. And some spec sheets for pressure relief valves will refer to that as pressure override. But override being the critical term here that describes what is the differential. What's the difference between the cracking pressure and the relief setting? So in this case, it looks like, what's the number? If you're looking back at the scale there on the left-hand side, guys, who wants to chime in? What's the value of our pressure override here?
Looks like it's 500.
Yeah, thanks, Nathan. Yeah, the pressure override value is 500 psi. Now, here's a question for you, and I'll let you experiment with the controls to figure this out. Does that pressure override value change if we maybe change the relief setting? Go ahead and play with that relief setting that's maxed out right now. Don't change your resistance. Leave your resistance maxed, but go ahead and just move that relief setting up and down a little bit. Take a moment to observe that. What happened? Did the difference between cracking pressure and the relief setting, did that change?
Yeah, it doesn't look like it changes.
It doesn't, does it? That override is a function of this valve, its design, the single poppet aspect, the spring that was chosen, okay? For the most part, under ideal conditions, this pressure override really isn't going to change. And that's just a function of this relief valve. So you could say, hey, we can get rid of the override problem by lowering the relief setting. No. If we change the relief setting down to approximately 800, well, now our cracking pressure is 300. If we set our relief setting down to 700, now our cracking pressure is 200. So the difference is 500 because of the design of this system. And, you know, if someone was to come along in our production plant and say, you know, we need that hydraulic motor to turn at the normal speed when we're up at 980 psi. See, look at my system pressure gauge on the screen right now that I'm displaying. I'm close to 980 psi. Perhaps we need this hydraulic motor to turn at production speeds. You know, production manager's going to come along and say, oh my goodness, you know, we're down to only 1/20th of our production rate. We're going to go broke if we turn the motor at that speed. We need it to go faster when we're at 980 psi. Didn't you guys, you hydraulic experts, didn't you guys tell me that the system is safe right up to 1,000 psi? Why do we have to be in this terrible slow mode when we're at 980? So somebody unwittingly, not understanding the full aspects of what happens in hydraulics, maybe feeling pressured by the boss, what do you think they might do to this relief valve if they could? Who wants to take a guess?
Crank it up as high as it goes.
Somebody might come along
Max
and
it.
try to crank that relief valve, and to get back to full speed of that hydraulic motor, we're going to have to take that 980 and add another 500 to it. So to get back the full speed of that hydraulic motor, we might have to turn that relief valve up to what number? 980 plus 500? Yeah, about 1,480 psi. Wow, right? And if the original design engineer said, no, this system won't be safe above 1,000, then we should not ever be adjusting above 1,000. But how do we make that boss happy who said the system should run at normal speed right up to 980? Is there a way? Absolutely. So let's find out if we can get a relief valve going that'll be a little bit more sensitive to this situation where we need full production speed for that hydraulic motor right up to the point at which relief action is needed. So let's go back to session. And in the simulations, let's now find the anatomy and behavior of a relief valve that's balanced and pilot operated. It's the third one in the menu. Let's bring that one. Just going to get things the way I want it here. So things are getting a little bit more complicated. We've moved from the type of relief valve that has only one spring and one adjustment, and now we're moving to a little bit more complicated relief valve that's got a number of mechanical elements to it. It doesn't have to be that cast iron type relief valve I was just showing you. 2 springs and 2 poppets can even be built into these small thread-in style cartridge valves. Maybe we'll have a look at one of those. So when you look now at the screen, what do you see? Well, just like before, you'll see there's a bit of a system schematic on the left. We've still got that pump that we had before, 20 gallons per minute flow. We've still got our hydraulic motor with the brake shoe brick stacker, whatever it was doing, producing motion for our factory or our machine. And then we've got the relief valve. But have a look at both the cutaway and the symbol, and just take a moment on your computer, your tablet, to move around and hover over various different items that you see in the schematic symbol and look for their equivalent component lit up over on the cutaway. And if you want to zoom in, go ahead, guys, and zoom in all you want to study these pieces up close. And so what have you observed? It's a little bit more complicated looking. I promised you a relief valve that has 2 poppets and 2 springs, and I think you could see them. There's a main poppet here, the P port coming in from the system, the pump, and there's a spring. There's those little 2 rows of circles. And hang on, what's with that spring there? That spring says it's only 50 psi. That doesn't sound like a very strong spring. Someone was asking earlier, I think it was Robin early in our lesson, she was asking, hey, how stiff is that spring? Well, this particular spring now that we're looking at here is only a 50 psi equivalent spring. If you had that one in your hand, you'd be able to squeeze it quite easily in the palm of your hand, that particular one. And that's holding our largest poppet closed from the pump path back to tank. Now, up in the top half of this relief valve is something new. We have a whole second component to our relief valve, and that's called the pilot section. So whenever you read on a specification sheet for a machine or for a relief valve that it's pilot operated, you need to imagine that there's an entire second section to this component somewhere that has a function that's meant to pilot or control the main poppet. And that's what's happening here in this upper section. And if we were to take the spring out of that one, we'd be back to that same spring we were talking about early in the lesson. That would be a spring that's very stiff and very difficult to squish in the palm of your hand. It would have high pressure override, but that's not really going to bother us much because we're only going to need to unseat this pilot poppet a little bit at the right moment. We're going to have highly restricted flow going through the pilot section because of the balance orifice. Okay, let's do some playing. The best way to learn is to play with this simulation. So I'd suggest you let's crank the relief valve up to the top again, because I think that'll be a great way for us to compare similar numbers as our previous simulations. So crank it right up there. Let's walk that resistance up to 500 and change, just like we did before. Get to 500 and anything as a system pressure value. This time, it didn't crack open, right? In our previous example, we had flow passing through that relief valve back to tank just as soon as we were past 500. It didn't happen. Let's go up to 750 psi pressure on the system gauge. In our previous example, guys, we had 10 gallons per minute of our 20 gallon per minute pump. We're going through the relief valve. We've got no such thing happening here. Play around with that for a bit and see if you guys can discover what the cracking pressure is of this relief valve. You may not get right on the exact number, but I think you'll figure it out. And hint, look at label names and numbers for the parts in that cutaway.
I think it's the same as the spring that's in the main poppet.
Yeah, that spring that's in the main poppet is kind of a key component for figuring out our cracking pressure. Absolutely right. So this relief setting, when you dial it all the way to the right, just like our previous examples, it's set at 1000 psi. Just for learning purposes, we cheat and tell you that right here above the blue control knob, it says it's set at 1000 psi. But you guys already know that in order to really set a relief valve, you're going to have to see it somewhere on an active pressure gauge. That's the only way to really know if you're working on machinery. But for the moment, we see it set to 1000 psi. And what Ivan has figured out is that we crack open somewhere just above, somewhere right around 950. Yeah, absolutely right. That's a 50 psi spring in there. And so isn't this great? This is where the mysteries of the pilot-operated relief valve come into play. So let's think about how this relief valve actually works for a moment. Let's forget about the symbol over on the left side. I'm just going to zoom in on the cutaway part of the relief valve for a little bit. Maybe that was too far. There we go. And I'm going to turn my resistance back down. I'm going to close up my relief valve for a second by getting rid of my resistance. And we're just going to think about the relief valve in its normal state. Maybe something I didn't mention before about the symbol, and I'll do it now, is that the relief valve is typically drawn with the poppet out of alignment from the inlet port to the relief valve to the outlet. That relief valve poppet, that arrow, is sitting out of alignment down at a rest position that the spring forced it to go to. So a lot of people speak about a relief valve as being a normally blocking or a normally closed type of pressure valve. It's not passing any flow through it until you get it into its active state. So normal on the drawing, if it's all black and white, normal is when the relief valve is at rest and it's not being asked to be active. So that's how we see it here. If I go back to the cutaway, we see that that main poppet is closed up, and you guys might say, you know, it'd be a perfectly logical question for you to chime in and say, hey, Carl, how could a 50 psi spring ever keep this poppet closed in the face of 900 psi of pressure coming underneath? How would we ever keep that poppet closed? So study the color area and see if you can come up with an answer for me. Study that same color field of yellow that we're in right now. Who wants to take a shot at this?
Additional to the spring, we have pressure applied on the top of poppet.
We have pressure applied to the top of the main poppet. Quite right, Alex. There's pressure applied to the top of the main poppet. When we are at a standstill in that there's no flow passing through the relief valve, maybe the pump is still sending flow somewhere else, but if there's no flow passing through the relief valve and the relief valve is closed, then whatever the pressure is on the inlet port follows through the balance orifice. An orifice is not an active component in hydraulics when there's no flow passing through it. They get really dynamic once there's flow, but if there's no flow, it's just part of that world of Bernoulli's that we studied at the very beginning of our hydraulics course, and that is we're in a state where the pressure is the same everywhere if there's no flow. So we follow it through and into the top of the main poppet, and we find out that the same the same pressure value can be acting on this annular rim at the top of the poppet, can be acting on the surface area inside the bottom of the poppet here. All of that together with the spring actually turns out to be stronger than nearly the same area on the bottom. Okay, little bit less area on the bottom, but pretty close to the same amount of surface area on the bottom. Alex is right. We have an advantage. Surface area from the top, pushing down, holding it closed. So it only takes a small amount of additional force, the bias, from that 50 psi spring to keep it shut. And then, as resistance increases, I'm going to stay zoomed in here now. You guys already know what's happening on the hydraulic motor. We're stacking bricks. And when we get to a point where the pressure is just above 950, then all of a sudden we'll find out that the pressure was high enough here in the pilot section to slightly unseat that pilot poppet against the resistance that was dialed in when someone made adjustments to this relief valve. We only need a tiny amount of flow to be passing through the pilot section for there to be a pressure drop here. Whenever we have a small orifice in a hydraulic system and flow starts to move, you will have a pressure drop. So the pressure will be higher before the orifice and lower after, because there's less resistance after the orifice. Is there still resistance? Absolutely. There's this pilot poppet, but that's the only resistance left. Meanwhile, back here in the red area at the entry to the relief valve, we still have two resistances in series. We studied series and parallel resistances earlier in the hydraulic course, but here it is again happening in a very dynamic fashion. We've got an orifice which is a resistance dropping our pressure part way down. And so now we don't have the same amount of force together with that spring as we had before. And so our main poppet has cracked open slightly, and some of our flow from the pump is being directed back to tank. But it's only happening just as we creep up on our relief valve setting. Go ahead and run your resistance slowly up to the top. It's pretty hard to do because this relief valve is very responsive. Between 955 and 995 and 1,000, that main poppet goes all the way open with very small amounts of pressure change in the upper half of that main poppet. So lots of design dynamics there for the designers of these relief valves. But for you and I, what's really important to wrap our heads around, if we zoom back out, is that slope line from cracking pressure to full relief setting has become almost a flat line. The pressure override is what? Is it really large or really small now in the new relief valve we're looking at? What's happened to our pressure override value?
Small.
Very small, absolutely. Very small pressure override. And so going back to a story I was telling you earlier, what if production wanted that hydraulic motor to spin at production speeds? Quite normally, right up close to the high 900s. This is the relief valve you're going to need because with very little amount of pressure back down, just below, there we are, I'm at 948, just below 950, we're back in full production in the plant. All 20 gallons per minute from our main pump are headed through our motor. The production boss is happy, and we have a relief valve that's still set to protect us from harm or protect the system from destruction as soon as we get to that all-important 1,000 psi. Isn't that cool? Neato, hey? So you probably have a few questions starting to develop in your mind, but one of the things I should point out right off is that if the draftsperson who draws your hydraulic schematic was to be fully interested in details and being fully honest, they would draw the relief valve similar to what is shown here. They would show that there is inside the relief valve, which is the bounding box in light gray here with the two dashes, letting us know that this is all one assembly. And they would honestly show you that there's actually two relief valves built into one. But one of those relief valves has an adjustable spring, so you know which one that is. And one of our relief valves does not. It has a fixed value spring. And feel free to run your slider back and forth again, your resistance slider, and just watch the relationship between those two relief valves built into one. And look at that balance orifice. I think you can appreciate why that's drawn into the schematic symbol. Okay, let's take some questions. What's anything come to mind, you guys? What questions do you have for me?
Is there a kind like an even better kind of relief valve where the spring inside the main poppet is adjustable, or do you always have a fixed spring in that main poppet?
Oh, interesting thought. There are relief valves that let you select from the beginning for the same model series, select a slightly different spring for the main poppet. And there's a couple of different reasons why you might do that, but I don't think in my travels I've ever come across any adjustable springs for the main poppet in a pilot-operated relief valve. That one's buried down inside, and the design function of that valve has been set. So yeah, all the adjustment is just up there on the pilot section. The reason to select a different mainspring, here's the main poppet, from this particular design, a relief valve, and you'll see this Eaton style in the menu of simulations. This is the main poppet. It's typically a 20 psi spring, but they'll let you select a heavier one. I think it's a 75 or an 80 in case you need to reserve a higher system pressure for piloting functions when you're in relief mode and you still want enough pressure held back on the pump side to do some piloting.
So is there any way to have a relief valve where you can adjust the override? Or is the override only a factor that you choose when you're picking the relief valve, and then once you've chosen your relief valve, you're stuck with that override range?
Yeah, no, to be clear on that, the override is chosen when you select your valve. So once the valve has been specified for the system, that's the override you're going to get.
Why doesn't the flow just all go through that top relief valve and bypass the middle one entirely?
Yeah, that's a good point. So let's see here. Our pump says it's rated for 20 gallons per minute. I see that on the schematic. That balance orifice, if you take it out, will typically be somewhere around 0.020 to maybe at the very maximum for some really big relief valves might be 0.040 of an inch, 20 thous of an inch, 40 thou of an inch. It's a very small orifice. And so in working with a 20 gallon per minute pump, you're only going to be able to get a very small amount of flow through that orifice if the valve is designed to open a much bigger poppet somewhere else. And that main poppet is rated for the flow we need. The valve is carefully designed. Could you get 20 gallons per minute through that tiny orifice? Yes, but that's so hard to do. And this valve has been designed to make sure that that main poppet, which is large, will open long before you could pass that kind of flow through a tiny, tiny spark plug. If you know spark plug gap, it's small. Yeah. All right, so we've covered a few things that bring the relief valve into play today. And one could go on and study a number of other facets just to maybe give you a little coverage as to what else we're going to do in future lessons. We'll find out that the same types of principles are at work inside very small screw-in cartridge valves. You guys see these threaded into manifold blocks. Helps us get rid of lots of extra hoses and hydraulic lines and fittings. There it is again. 2 springs, 2 poppets. The same types of actions and principles are at work. So when you see a very small cartridge, very easy to say, oh, it must be direct acting. How could they? No, they fit all that stuff inside a small cartridge valve too. So feel free to play with those as we are continuing our study during our classes together. You may also want to come back for our lesson on using that vent port. If you noticed in the previous lesson, we had a blocked off port, a vent port. It had a little X on it in the schematic. And here we are finding out that we could take a balance style pilot operated relief valve and hook up a remote control to it. And on an operator's console somewhere, someone could be remotely setting. We're still setting the main poppet. It's still inside the main relief valve. But if we set things carefully, a remote pilot section at a distance from the main relief valve could actually be used to set the main system pressure. And there's lots of other interesting variations on the theme too, like this one. Here's a really interesting one where now we are actually remote controlling by not using the vent port, which is before the poppet in the pilot section. We're actually remote controlling by restricting the flow coming off the drain. Some relief valves offer a drain, and that's quite often labeled port Y, or on a cartridge it would likely get labeled port number 4, and you could actually resist off the drain and do some remote controlling. And that's for our more advanced lesson to come on remote controlling of pressure relief valves. Any other questions before we finish off today's lesson?
Can we go ahead and play with these simulations ourselves before the next lesson if we're curious about that?
Absolutely. That's a great thing to do. And there's a whole series of them there. So feel free to experiment wildly with them. And then once you're done that, I'd like, once you've gone through the lessons and all the simulations, I'd like everyone to go ahead and write the relief valve quiz. And we'll see how everybody does on knowledge for pressure relief valves.